If you want to know whether adding a rear wing to your FSAE car is actually worth it, or whether a heavier battery pack will cost you more time than the extra power saves, you need a lap time simulator. So I built one from scratch. Let me show you how it works. The simulator is a point mass model. That means the car is treated as a single point that contains the parameters of the vehicle, which means that there's no suspension, no tire flex, no weight transfer under braking, just forces, Newton's second law, and friction limits. This all sounds like a big simplification, and it is, but here's the thing. For an FSAE car, it predicts lap times within a few percent of reality, and it runs in milliseconds. That's the trade-off. A full multi-body simulation takes hours to set up and still has model uncertainty baked in. This one is fast enough to sweep across dozens of design configurations in seconds, which is exactly what you need when you're making trade-offs early in the design cycle. At each step, time advances by 10 milliseconds. Every step, the solver asks one question: is the car going too fast for this segment? On a straight, there's no cornering limit, so we accelerate. Drive force is the smaller of the two things, the engine's power divided by current velocity, which is the force the drivetrain can actually deliver at that speed, or the longitudinal friction limit, mu x times mass times g. Whichever is smaller is what you've got. Subtract the aerodynamic drag, which goes up with the square of velocity, and that gives you net force. Net force over mass is acceleration. On a corner, speed is physically capped. The maximum speed you can carry is the square root of mu y times g times the corner radius. That's just the circular motion equation. It's the speed at which your lateral friction is completely saturated. If the car is above that, it brakes at full mu x deceleration until it's back under the limit. Here's the part I want to spend a second on, because it's the most non-obvious piece. Look ahead braking. If the solver only checked the current segment, the speed trace would look wrong. The car would be at full acceleration right up to the corner entry, then instantly drop to corner speed. That's not physically possible. You need a brake zone. So for each corner, the solver works backwards. It calculates whether the car, at its current speed on the current straight, can actually stop in time to hit the corner entry at the right speed. If the answer is no, it starts braking early. That's what produces the realistic speed trace with a proper brake zone before every corner. It's a small thing in the code, but it's what makes the output actually believable. Everything in the model comes down to 5 parameters. Mu x, longitudinal grip, controls braking and acceleration. Mu y, lateral grip, the single biggest lever on corner speeds. Power, this limits the top speed on long straights. Mass, affects how quickly forces change velocity. Drag, sets terminal velocity and costs time on fast sections. The real value is being able to sweep these independently. Want to know how much lap time a 5 kilogram weight reduction buys you? Run it. Want to compare 2 aero configurations with different drag and downforce trade-offs? Run both and look at the differences. That's the simulator. A 10 millisecond time step, tracking limits, and look ahead braking. It's a simple model, but simple models that are fast and interpretable are often more useful than complex ones you can't reason about. Next, I want to add aerodynamic downforce as a speed-dependent grip multiplier, and eventually pull real data from track geometry, as well as GPS data instead of hand-defining segments. If you want to see the code or dig into the math, I'll link it below. And if you're building something similar, drop a comment. I'm curious what other approaches people are taking.